In this lecture, we discuss multiplication and division of complex numbers in relation to their polar representation. Let z be equal to x plus y times I, where I squared equals minus 1, so that I is a square root of minus 1. Let x and y be real numbers, so that x plus y times I is the standard form of z. The absolute value of z is equal to the square root of x squared plus y squared. As an example, the absolute value of e raised to the power I times theta, or the absolute value of cosine theta plus I times sine theta, is the square root of cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is of course 1, so that the absolute value of e raised to the power I times theta is 1. On an added note, when we say the square root of a positive real number without a negative sign in front of the square root sign, we mean the positive square root of the real number. If we want a negative square root, then we put a minus sign in front of the square root sign. It won't be quite the same, however, for the square roots of imaginary numbers, which do exist. Let an argument of z be theta, so that z equals the absolute value of z times e raised to the I theta power. Since e to the I theta power equals cosine theta plus I sine theta, z is also equal to the absolute value of z times the quantity cosine theta plus I times sine theta. Let z sub 1 be equal to x sub 1 plus y sub 1 times I, and let z sub 2 be equal to x sub 2 plus y sub 2 times I, where x sub 1, y sub 1, x sub 2, and y sub 2 are all real numbers. Let an argument of z sub 1 be theta sub 1, and let an argument of z sub 2 be theta sub 2. Therefore, z sub 1 equals the absolute value of z sub 1 times e raised to the power I times theta sub 1, and z sub 2 equals the absolute value of z sub 2 times e raised to the power I times theta sub 2. Then, z sub 1 times z sub 2 equals the absolute value of z sub 1 times e raised to the power I times theta sub 1 times the absolute value of z sub 2 times e raised to the power I times theta sub 2. We still add exponents of exponentials when multiplying exponentials with the same base, even when the exponents are imaginary, so that z sub 1 times z sub 2 equals the absolute value of z sub 1 times the absolute value of z sub 2 times e raised to the power I times theta sub 1 plus theta sub 2. Recall that z sub 1 times z sub 2 is equal to this polynomial expression. The viewer can check as an exercise that the square of the absolute value of z sub 1 times z sub 2 is equal to this quantity. This factors out into the quantity x sub 1 squared plus y sub 1 squared times the quantity x sub 2 squared plus y sub 2 squared, which, as we can see, is this time the square of the absolute value of z sub 1 times the square of the absolute value of z sub 2. Therefore, the absolute value of the product of z sub 1 and z sub 2 equals the product of the absolute values of z sub 1 and z sub 2, so that we can refer to the absolute value as a multiplicative operator. Multiplication by the absolute value of z sub 2 could be a dilation or a contraction. We have a dilation if the absolute value of z sub 2 is greater than 1. And we have a contraction if the absolute value of z sub 2 is less than 1. Observe that the argument of z sub 1 times z sub 2 is now theta sub 1 plus theta sub 2, so that the argument of z sub 1 is increased by the argument of z sub 2 upon multiplication by z sub 2. Increasing the argument by theta sub 2 is a counterclockwise rotation by the angle theta sub 2 around the origin. Therefore, multiplication by a complex number is a composition of a rotation with a dilation or a contraction. If the absolute value of z sub 2 equals 1, which means that z sub 2 equals e raised to the power I times theta sub 2, then multiplication by e raised to the power I times theta sub 2 is a pure rotation. Let z sub 3 be equal to z sub 1 times z sub 2. Then the absolute value of z sub 3 equals the absolute value of z sub 1 times z sub 2, which, as we had just seen, is the absolute value of z sub 1 times the absolute value of z sub 2. Let us suppose that z sub 2 is non-zero. Then the absolute value of z sub 3 divided by the absolute value of z sub 2 equals the absolute value of z sub 1. Since z sub 1 equals z sub 3 divided by z sub 2, we find that the absolute value of z sub 3 divided by the absolute value of z sub 2 equals the absolute value of z sub 3 divided by z sub 2, so that the quotient of the absolute values of two complex numbers equals the absolute value of the quotient of the two complex numbers as long as we are not dividing by 0. Now let alpha and beta be two real numbers. E raised to the power I alpha times e raised to the power I beta is equal to e raised to the power I times the quantity alpha plus beta, where we added the exponents and factored out I in the exponent. According to Euler's formula, e raised to the power I times alpha plus beta is equal to cosine of alpha plus beta plus I times sine of alpha plus beta. We apply Euler's formula again, but this time individually to e raised to the power I alpha and to e raised to the power I beta. Their product is equal to the product of the quantity cosine alpha plus I sine alpha and the quantity cosine beta plus I sine beta. Expanding this product, replacing I squared by minus 1, and writing the result in standard form, we get this expression. These two expressions are equal if and only if the real part here equals the real part here, and the imaginary part here equals the imaginary part here. And so we obtain the sum of angles formulas for cosine and sine. Now, if beta were to be equal to alpha, then we would have the square of e raised to the power I alpha. This should be equal to the square of the quantity cosine alpha plus I times sine alpha. Applying another law of exponents, this time to the square of e raised to the power I alpha, the square of e raised to the power I alpha equals e raised to the power 2 times I times alpha, or e raised to the power I times 2 times alpha. Euler's formula says that e raised to the power I times 2 times alpha equals cosine of 2 alpha plus I times sine of 2 alpha. Therefore, the square of the quantity cosine alpha plus I times sine alpha equals cosine of 2 alpha plus I times sine of 2 alpha. We can extend this result so that if n is any positive integer, the quantity cosine alpha plus I sine alpha raised to the nth power equals cosine of n alpha plus I times sine of n alpha. According to the third edition of the text, A Complex Analysis by Lars Alfors, this equation is referred to as DeMoivre's formula. It then follows that if the argument of z is theta, then z raised to the nth power equals the absolute value of z raised to the nth power times the quantity cosine of n theta plus I times sine of n theta. As an exercise and an example for this lecture, we simplified the quantity 1 plus I raised to the 200th power. 1 plus I corresponds to the point 1, 1 on the complex plane, so that we can set the argument of 1 plus I equal to pi over 4. The absolute value of 1 plus I, or the distance of the point 1, 1 to the origin, equals the square root of 1 squared plus 1 squared, or the square root of 2. So 1 plus I equals the square root of 2 times e raised to the power I times pi over 4. Hence, the quantity 1 plus I raised to the 200th power equals the quantity the square root of 2 times e raised to the power I times pi over 4 raised to the 200th power. Square root of 2 is 2 raised to the half power, and 200 over 4 is 50. So that the quantity 1 plus I raised to the 200th power equals 2 raised to the 100th power times e raised to the power I times 50 pi. E raised to the power I times 50 pi equals cosine of 50 pi plus I times sine of 50 pi. Cosine of 50 pi is 1, and sine of 50 pi is 0. Therefore, the 200th power of 1 plus I equals 2 raised to the 100th power.